theorems about roots of polynomial equations. It's a little wordy, but it's actually fairly easy. So let's look at the concept. Let p of x equals a polynomial, basically, and the coefficients are all integers. And it says that if the polynomial equation p of x equals 0 has any rational roots, if it has any rational roots, then each rational root is in the form of p over q. So if the polynomial equals 0, and if it has rational roots, the rational roots is in the form of a fraction. And what is that fraction? The numerator, p, is the factor of the constant term. So the constant term is here, right? And q is a factor of the leading coefficient, an. Okay? So if I were to write this out like this, so p over q is it's the rational root, and then p is the factor of a0 over q is the factor of the leading coefficient, an. Now let's look at a real example here. So in this example, it says from the graph, it appears that 4, which is right here, 4 is a 0 of the function p of x equals 8x to the 5th minus 32x to the 4th plus x squared minus 4. Without substituting, how can you determine if p is a possible solution to p of x equals 0? So our natural instinct is to plug it in. So here it's saying don't plug it in. And then therefore we have to use something different. And that's when we have to use the rational roots theorem. And to do that, I need to first figure out my constant term. So constant term is 4. And my leading coefficient is 8. Okay, now I'm going to have to factor each number. So for 4, I would have, I'll change the color, I'll have positive 1 and negative 1, positive negative 2, and positive negative 4. For 8, I have the same, and I have one more, positive negative 8. Okay, so you have to list this out first. And then the rational roots theorem states that the possible rational roots of p of x equals 0 are the following. So here is my possible rational roots of p of x equals 0 are. This is where I play a little trick, okay? You notice that the denominator should be the leading coefficient, and there are 4 terms, right? So I'm going to write each number in my constant term. So positive negative 1, I'm going to just take the positive. So I'm going to write it 4 times. And I'm going to do the same with 2. And then, is that 4? That's 3, 4. And then I'm going to do the same with last one, 4. Okay, now, okay, that's my, I got the color reversed, but that's all right. You got the concept. That should be in red. Now I'm going to put in my denominator. We said the denominator is the leading coefficient. So that would be 1, positive, negative. This is 2, this is 4, and this is 8. And so for 2 is 1, 2, positive, negative, positive, negative, positive, negative, 4, 8. For 4 as well, 1, 2, 4, 8. I cheated a little bit because whatever the terms are, I always put in positive and negative. I got both positive and negative world covered, so then the rest of it I just played a little trick just to make it a little bit faster. Okay, I hope this makes sense. But review possible rational roots theorem says that it has to be in the form of constant, a factor of the constant over a factor of the leading coefficient, and this covers all possibilities of the factors, right? Because the values in the numerator are factors of the constant term, and the values in the denominator are all the factors of the leading coefficient. Now let's look at this. So again, go back and revisit the question. The question says, without substituting, can you determine if 4 is a possible solution to p of x equals 0? So if you skim through the answers, the possible solutions to this polynomial, you quickly find out that right here, positive and negative 4 over 1, but we're only asking about positive 4, is amongst the mist of possible solutions. Therefore, the answer to the question is yes. 4 is a possible root of p of x equals 0. Okay, sorry about my handwriting. It looks like chicken scratch on paper. But the way to double check it is very easy. Substitute 4 in there, see if you can get an answer or not. All right, quick review, really cumbersome in terms of thinking things through, but in terms of operating, pick out the leading coefficient, pick out the constant term, figure out all of their factors, then factor of constant terms goes into the numerators, and factors of the leading coefficient goes into the denominators. To cheat, ignore the signs, give positive and negative to every single possible root, and you spread it out, and then you figure out which one is the possible root amongst all of them. Okay, let's look at this problem. A storage company is designing a new storage unit. Based on the dimensions shown, the volume of a container is modeled by the polynomial v of x equals 2x cubed minus 7x squared plus 6x, where x is the width in feet. What are the dimensions of the container in feet if the volume of the unit is 154 square feet? So what this is saying is I want 154 is the volume, and that should equal 2x cubed minus 7x squared plus 6x. And that's the setup, right? And if I want to swing the 154 over, I can set the polynomial equal to 0, and I can solve it from there. You haven't learned how to solve this, and we're looking for possible solutions in this unit. So what you do is that at this point, you're going to throw this polynomial into your Desmos graphing calculator or your TI-84. I much prefer Desmos. These days, Desmos are all embedded in your SAT exams, so make sure that you're comfortable with it. And if you use your Desmos, you're going to vaguely see where the solutions are. That gives you some idea. So this is the first step. Now, second step, I'm going to use my rational roots theorem to figure out what are the possible rational roots. So my constant term is negative 154, right? And my denominator should be my leading coefficient, which is 2. Oh, this is annoying. So 154, I will have 1, 2, I would have 7, 11, 14. By 14, that's 22. Yes, 22 works too. 77, and then 154. I think this covers it all. These are all my possible factors. Now 2, obviously. It's 1 and 2. You can play with it. Like I said, then you have to, excuse me. But as you can tell, you're going to have a long list of possible solutions. And this is why throwing the polynomial into a decimal graphing calculator will show you what are the possible ones. It looks to me that it's somewhere around 5. And for us, probably the possible solution would be, sorry, I was touching that. That should be probably 11 over 2 is the possible solution. That's from just graphing it in the calculator. So I have to verify whether 11 over 2 is the possible solution or not. Remember, we do this with synthetic division, so we have to take the coefficients down. I think that's negative. And then my factor is 11 over 2. So the first leading coefficient comes down. And then this would be 11. That's 4. 4 is 22. That's 28. Then that's 154. So I have 0 remainder. Perfect, which means that my x minus 11 over 2 is a factor to the polynomial, and the remainder of that polynomial is 2x x squared. It will be 1 degree down, plus 4x plus 28 equals 0. Okay, now I'm not done yet. I have to keep solving this. I've got one answer, that's 11 over 2, but I have to solve 2x squared plus 4x plus 28. You can do it on this side. You know, if you factor the 2 out, it may make life easier. It becomes x squared plus 2x plus 14. This is not factorable, so you have to find the discriminant, b squared minus 4ac. b squared minus 4ac would give you negative 208. Therefore, there's no real zeros for this factor. Okay, for this quadratic equation, there's no real zeros, which means 11 over 2 is the only real solution. To v of x, the original equation. Okay, so you have to interpret it. It's asking you what are the dimensions of the container in feet. So you have to say the width of the container, which is x, is 11. So width of the container is 5.5 feet, 11 over 2. Right? Speak English. Don't just speak mathematics. I love it when you speak mathematics, but try to speak English here. And the width is 11 over 2 minus 2. I'm sorry, the length uh, 11 over 2 minus 2 is 3.5 feet. And height is 2x, isn't it? Yep, 2x minus 3, which is 8 feet tall. That's the conclusion there. Okay, so if you want to box that, that's your final answer. That's it. Okay, here is another theorem called Fundamental Theorem of Algebra. This is the reason that people don't like math. I hate this language here, but let's read it first. If p of x is a polynomial of a degree of n is equal or greater than 1, then p of x equals 0 has exactly n solutions in the set of complex numbers. If p of x has any factor of multiplicity m, count the solution associated with that factor m times. For example, the equation x minus 3 raised to the fourth power equals 0 has 4 solutions, each equal to 3. That's a lot of word saying something very, very simple. So what it's saying is that if I have any kind of polynomial, say p of x equals a cube function, something like this, right? And then there should be 3 solutions. If p of x, the highest degree is 5, then it should have 5 solutions. That's plain English that people can understand, on the condition that n is greater or equal than 1. Obviously, linear equations has 1 solution, right? And so when people are asking, what about x minus 2 squared? 2 solutions. They're exactly the same. X plus 5 raised to the 8th power. 8 solutions. Then you have to repeat negative 5 8 times so that it's consistent. That's all there is. It's not hard at all. Here is a relatively easier but laborious problem. It's asking us to find all the complex roots of the polynomial function. So to do that, we first have to find the rational roots first by using rational roots theorem, right? So here I listed the constant terms and the factors of the constant term and the factors of the leading coefficient. And then this is a relatively easier one. I like this much better. You just list out the possible rational roots using both positive and negative signs. And then you test it out. You can use your calculator at this point, but it looks like 2 over 3 and negative 1 may be the roots. So you have to test it out, right? Making sure that 2 over 3 is indeed the root, and so is negative 1. So if you look at this step here, you will see that both of them are factors. Now, remember, once you test out that it is a factor, that 2 over 3 and negative 1 is indeed a factor, then the remainder of the quotient gives you the other factors. So you just keep factoring them out like that. And now you're breaking down a pretty long and complex polynomial into 2 binomials as well as a quadrilateral, quadratic equation. It's getting too late here. I'm recording this at 9 o'clock at night, so that's what happens. Anyways, as it turned out, x squared plus x plus 1 obviously cannot be factored, so you have to use the quadratic formula to find the last 2 roots. And as it turned out, the last 2 roots is a conjugate of a complex number. So again, use what you've just learned. The fundamental theorem of algebra states that because the highest degree of this polynomial is 4, we're expecting to have 4 solutions. They might be identical, which doesn't apply in this case, but it is 4 solutions. We have 2 real roots and 2 complex roots. Okay, so I didn't work this out with you because I think their explanation is pretty straightforward. So in this page, we're going to analyze how are the types of zeros of a polynomial function related to the coefficients of the polynomial. And here's the first problem. Suppose a quadratic polynomial function p has one rational zero c and one irrational zero a plus square root of b, where a and b are rational numbers. Are all the coefficients of p rational? So this is a really fancy way of giving you some background information. What it is saying is that we've got c here, that's a factor, and we've got a plus square root of b, that's a factor. So, and we also have a polynomial. So if I want to write it out, I said I've got c, so x minus c is one of the factors, and x minus a plus root b would be the second factor, right? You do some expanding, let's see. This would be a plus root b plus c. Yep, there it is. Sorry, it took me a while to think that through. This would be a plus root b c. So I just multiplied and collected the terms. You can do it more step by step if you want. I went for some shortcuts there. Make this look prettier. So what do we have here? The question is, what are all the coefficients be rational? And let's look at that. So oops, coefficient here is 1. This is not rational. This is obviously not rational, right? So the answer is no. P of x has 2 irrational coefficients. Okay. I think in your textbook there is another part of the same example that's asking about if a quadratic polynomial function has 2 irrational zeros, and obviously they're conjugates, a plus square root of b and a minus square root of b are all the coefficients of that function, of that quadratic is rational. And if you follow the same approach, do the same simplifications, you will find out the answer to that is rational, which makes sense, right? Because we've dealt with all sorts of quadratic functions that cannot be easily factored. And for some of them, when we use quadratic formula, we end up with a pair of complex solutions. But their coefficients are always rational. You don't see irrational numbers in those very easily. Okay? So keep in mind, this is something that if you understand it, it will help you do quick checks down the road. So for quadratic functions, if they have one rational zero and one irrational zero, a plus root b, right, where a and b are rational, and they will have some irrational coefficients, which is the example we just did. But a quadratic with a conjugate pair of irrational zeros of a plus square root of b and a minus square root of b, they will have only rational coefficients. If you do some of these calculations and make careless mistakes, that's when you look at the final solutions, and it doesn't make sense. That's usually is the time you have to go back and check your calculations. This is a very useful conclusion of what we just practiced. Basically says that if I have a polynomial function, if a plus root b is a root when p of x equals 0, then a minus root b has to be the other root. So the conjugates come in pairs. And if a plus bi is a complex root to the polynomial, then the conjugate a minus bi must be a solution to the polynomial. Okay, it's pretty intuitive and it's very helpful. And this is an easy and quick application of that conjugate theorem. It's asking, what's the quadratic function p with rational coefficients in standard form such that p of x equals 0 has 2 plus 5i as a root? So it's asking us to write the final quadratic equation function in the standard form, but it's giving us one root of 2 plus 5i, therefore 2 minus 5i, that's a 5. 2 minus 5i must be the other root, right? So now I have two roots. I can put them in as my factors. So P of x equals x minus 2 plus 5i times x minus 2 minus 5i. You do the simplifications of that. So that's, I'm just going to do a quick, so this is, final answer should be x squared minus 4x plus 29 equals P of x. So the equation is a quadratic equation with 2 plus 5i and 2 minus 5i as roots. This is my final answer here. Okay. So this is the concept summary for this unit. It's got a lot of information here. We went through quite a bit, spent quite a bit of time on rational root theorem. Remember, rational root theorem points out the possible solutions by using the leading coefficient as well as the last term, the constant term in your polynomial function. And after that, we moved on to the fundamental theorem of algebra, which is in plain English means whatever the highest degree of your polynomial is the number of roots that you should have for that polynomial. And lastly, we went through irrational conjugates and complex conjugates. It's quite a bit of concept. They're not hard. They're tedious. It takes practice. So take your time. Do not get frustrated, or at least when you get frustrated, you recognize that everybody else, certainly this is one unit that I don't like because it's so tedious. But the concept is there. As long as you get the concept, try to make sure you use the concept to do the deeper learning as much as you can. Okay? So last bit, as the fun slide for this unit, I decided to use this one. How to be more impressive. It's created by an anonymous person. Suppose we want to publish something that's as simple as 1 plus 1. That's not very impressive. If we want our article to be accepted by IEEE reviewers, so there must be some academic journal I'm not aware of, we have to be more abstract. So we could complicate the left-hand side of the equation, of the expression, by using natural log of e equals 1, and sine squared plus cosine squared of x equals 1. And the right-hand side can be stated as 2 equals sigma infinity from 0 to infinity of 1 over 2 raised to the n, so on and so forth. So read through this. By the end of this course, you should understand all of these properties, and that we probably will conclude it. We may not have 1 minus 10 squared y, but you will learn that in pre-calc. So to learn math, sometimes you can trick people by using something that sounds so foreign and unfamiliar. Replace that with something very simple and makes you sound really smart. I honestly think that a lot of math teachers use this trick. It's not that we're smarter than the rest of the world, we just know more jargons. And I have to say, as a former bond analyst, having worked on Wall Street, people always say, oh, I can't do finance. Really, it's just that all of these jargons that so many guys created a couple of 100 years ago at a bar near Trinity Church on Wall Street, they kept using those jargons until today. And that's what made it sound more impressive than the actual work itself. The actual work is actually no less impressive than natural log of e equals 1, or sine squared of x plus cosine squared of x equals 1. If you understand these, you can be on Wall Street and do whatever transactions that you want to do. All right, with that, I will see you in class. Bye.